in my paper, it's all the same points, but it goes further because it's a multi-step prediction. The simulation effect is so like it takes a measurement of current brain activity and uses that to make the board's prediction. There is
I see.
and so it's like a really important setup. So it should belong there, but it's such a risk.
Right. We get started? Hi everyone, welcome to lecture 3. Today we're going to be continuing supervised learning. And we will try to get through a lot of content again. But we're going to get into like some of the guts of imitation learning and try to see how to fix the multimodality problem and the compounding error problem, right? And so we'll do a quick recap, talk about why imitation learning is hard, and then kind of try to fix those challenges. Okay, so before we keep going, I'm a big fan of feedback control. And so in terms of like the class pace, too fast, too slow, or like just right? So like, anyone thinks it's too fast? Can you raise your hand? Okay, too slow? Just right?
I thought last time there were a couple of points where you could have slowed down and more precisely defined some of the symbols and walked through them.
Okay.
Absolutely. Sometimes I didn't keep up with it.
For sure.
The rest.
So the easiest thing at that point is just like interrupt me and tell me what which things are not clear, and then I'll just stop and expand it. No problem. Yeah.
In general, in this class, when you, I'm sure we'll see it later, but when you subscript the expectations, what does it usually?
It means that it's the expectation with respect to a particular probability distribution. So like, for instance, you're doing like expectation this thingy, right? Like, so you're asking like, what is the subscript, right? So it means that it's doing integral b of x f of x dx, right? So it's like, you're taking the expectation with the probability distribution as p, and the thing being you're taking the expectation over as f, right? And so it's the probability distribution that you're sampling from. Great. Okay. Any other changes that you all want in the class that we're not doing so far? It's only been 2 lectures, so there's not that much happening. But now's a good time to tell me. Okay, good. So, I mean, if you say nothing, I'm expecting all 5s in my course eval. So just remember that. Yeah. All right. So we start with Markov decision processor MDPs. You have states, actions, rewards, an initial state distribution rho naught, a discount gamma, and transition dynamics, P of ST plus 1 given ST80, which can be stochastic. We went to the Markov property, which says past is independent of the future given the present. And we define what a trajectory is, sequence of states, actions, rewards, states, actions, rewards that you take, that you get by like acting in the environment with your policy, which we'll define next, right? But that's the general formalism we're going to use. The goal of reinforcement learning is to learn a policy by theta, learn the parameters of a policy by theta to maximize the expected sum of rewards. It's an expectation because the dynamics are stochastic and the policy can be stochastic, right? And you're trying to take the expected sum of rewards along a trajectory and average it. So you get the policy that is best on average, right? And then we said, okay, reinforcement learning is too hard. So we're going to start by doing imitation learning. And the problem setting of imitation learning is that you're given some demonstrations of optimal behavior. So you're given state action pairs coming from an optimal policy. We're going to assume for now that the optimal policy is Markovian, right? Which means that the optimal policy does not need the history to act. It just uses the present to act. And if we get time, we'll get to why that might not be a good assumption and how to fix it. But essentially, the idea of behavior cloning is you're going to take states and actions. You're going to pretend that they weren't in a sequence, mix them up, treat them as IID samples, and do supervised learning, right? And that's what you call behavior cloning. And so essentially, you're going to take all of this data, mix it up, do supervised learning with PyTorch, or your favorite JAX or whatever the kids use nowadays. Then you just get your policy by theta, and you can execute your policy by theta in the environment, right? And so the point is, you essentially use all of the machinery of supervised learning, which means that you can use all your fancy neural network architectures, you can use all your fancy optimizers, and you're just going to treat it like a supervised learning problem. Right? So that's behavior cloning. Any questions? Okay. So the goal was to do behavior cloning. We talked about how we can just reuse all of the same machinery from supervised learning. So you can use the cross entropy loss or the mean squared error, anything that basically does maximum likelihood, and that's going to give us behavior cloning. So when we talked about why behavior cloning is hard, it's hard because we took a problem that is inherently sequential and we made it non-sequential, right? And so we took something where we actually want to act by rolling out the policy step after step after step. And instead of actually optimizing that objective like you would in reinforcement learning, you're optimizing a surrogate objective, which is saying you maximize the likelihood of taking the expert actions at the expert states offline, right? And so you'll note that these two are not the same. The important bit is that this expectation is under your data, your offline data. This expectation is under your else. Right? So this is saying act under your policy, see how well it matches the expert. This is saying consider all the data points in your offline data set, see how well you match your expert on those offline data points, right? But the important thing is that this data is not coming by executing the policy step after step after step, where this data is. Right? And so this kind of results in a problem called compounding error. Yeah.
Basically finding out our optimum policy is the right to evaluating its performance.
Yeah, exactly. So like in some, like this is the objective we're going to use to find the optimal policy. This is how we actually roll, like when you get a policy, you don't just like evaluate it on offline states, you have to run it in the world, right? So this is just saying run the policy in the world. This is saying how well did you match the expert? And this is the objective we're going to use. Now, the rest of the course is going to be about directly optimizing an objective like this. But right now we're going to say imitation learning optimizes this objective because it's easy, but it's not the same as this objective. And so when there's like a mismatch between what you train on and what you evaluate on. And this leads to this compounding error problem, where we said, okay, you're going to make a small mistake, go a little out of distribution, make a slightly bigger mistake, a slightly bigger mistake, repeat. And as you go further in your horizon, you get more and more further away from your training data. Right? And machine learning is, at least as far as I know, we haven't really figured out extrapolation. And so when you're outside of your training data, you tend to do crazy. Okay. Everyone with me on what compounding error is? Okay, good. We had a little informal proof. The details of the proof are a little less important. But the important thing is that if your policy is making, like it has an epsilon likelihood of making a mistake, right, in distribution, you're saying that at every step, you have an epsilon chance of making a mistake. And once you make a mistake, you go out of distribution, and all of the subsequent steps can be bad, right? And so you make a mistake, you go out of distribution, you have an epsilon chance of making a mistake. And if you make a mistake, you will continue to make mistakes from there on out. It's like a worst case problem, which means that you have an epsilon likelihood of incurring a cost capital H. If your cost is 1 per time step, if all of the time steps in the future are bad, you'll have H time steps that are bad. And you make such a mistake at every time step. So you have epsilon H times. Right? So you have epsilon H squared. Make sense? Yes.
So I'm not familiar with robotics, but for the expert data set, if you make an error going from like S to S prime, is there no way to know I've made this error going through the state because the data set is like in absolute terms before decision?
Yeah, like in some sense, the only thing that the model knows about the environment in this formulation is through the data. Right? Like it doesn't know anything about the world. It just has like some vectors going in, some vectors coming out, right? And so it doesn't really understand, like it's only seen this data, which means it doesn't really know what this means at all. Right? And so like you can expand the data set to cover that, but then there'll be something beyond that. There'll be something beyond. Right? So like the only understanding the system has of the environment is through the data. And so it doesn't really understand what it means to be there. Now, there's solutions we'll cover today, which are like essentially telling the system to like deal with OOD situations better. But right now, like at least this formulation doesn't say anything about how to deal with that setting. All right. So that's kind of a recap of what we were talking about. There's two parts to this error. The first is our epsilon, like how poorly we fit the training data, right? So like what is the likelihood of making a mistake? And the second is compounding error, which is quadratic and horizon, right? And so we're going to try and tackle both of these issues, but these are different issues, right? This issue is saying, if I had like pretty diverse training data, how well can I fit it? And the second issue is saying, even if I fit something to epsilon accuracy, I'm still going to have quadratically bad error with horizon, right? Even if you make little mistakes, those mistakes will get bigger and bigger and bigger. Okay, so that's going to like motivate our lecture outline. We're going to start by thinking about the first problem, which is underfitting, or there's going to be because of an issue called multimodality. And the second thing is going to be compounding error, right? So that's going to be how we cover it. And then we'll talk about some frontiers or some open, interesting problems. Yeah. Okay. So let's start with the first issue, underfitting. I know we talked about this a little bit last time, but we'll recap just for posterity. So the problem of underfitting is essentially, how do I reduce this epsilon, right? So if I have the likelihood of making a mistake is epsilon, right? In supervised learning problems, you make the model bigger, you make the model more expressive, and you often see performance gets better and better and better, right? So in language models or vision models or some time series, well, not time series, but like language and vision models, like you see often that bigger models do better. It's not always the case in behavior cloning. So why is that? It's because of what I've been calling distributional expressivity. It's mostly a term I made up, but it's kind of arguing that it's not just about the expressivity of your function approximator, it's the expressivity of your probability distribution, right? So if you remember, a policy is a combination. So a policy is going to take in a state. It's going to produce a distribution over actions. Yeah. And so a policy is a combination of our choice of our function approximator and our choice of our probability distribution, right? And so scaling up the model is often making this thing more expressive, making this thing bigger, and making your distribution more expressive is making this thing capture more modes or capture more complex probability distributions. So like we can consider lots of different choices for this P of A, right? So we said we're going to have the pi theta give us a P of A. Now this P of A can be, for instance, any one of these three or others. But essentially, like a Gaussian policy will take in pi theta, produce the mean and variance of a Gaussian. A categorical will take in pi theta and produce the logits for a categorical distribution. Diffusion model will take in pi theta and produce a noise vector, right? And so each of those will have different properties. So let's start by thinking about the Gaussian, which is the easiest one, right? Like a Gaussian is easy because, there's two parameters that define the whole Gaussian distribution. It's like doing supervised learning with a Gaussian amounts to mean squared error, so which is often what you do in regression. And so let's start by thinking about the Gaussian, right? So does anyone remember what the issue is with the Gaussian? If I'm doing behavior cloning with the Gaussian, why is it bad?
More average, like you
More
have
average.
two kind of outputs, like going left and right around the tree, and then
That's right.
you learn that you should go to the center.
That's right. Perfect. So this is my tree. And if you are going left and if you're going right, in your training data, if you have a mix of the left and the right, if you have a Gaussian policy, you're going to have a mode averaging problem because a Gaussian policy cannot represent multiple modes, right? Like there's no setting of the Gaussian that will give you essentially perfect matching for this thing. And so you'll have some left, you have some right. If it's a Gaussian, it's going to go straight to the middle. You have a collision. Now, no matter how big you make your neural net, you're still going to hit the tree, right? So you're gonna mode average. And so I'm gonna argue that the issue here is not just like the issue is mode averaging. The issue can be solved multiple ways. One of them is to making your policy distribution more expressive. So things like going from a Gaussian to a more expressive probability distribution, like diffusion model and so on. Or you can change the objective. Right now, we've talked about this maximum likelihood objective, right? Which is saying maximize the likelihood of A star at S star. And we'll talk about how you can change the objective and also deal with mode averaging in different ways. Right? So that's not the only, like having a more expressive distribution, not the only way to deal with mode averaging. Okay. So what I'm going to do next is I'm going to try and show that the objective, the maximum likelihood objective that we've discussed so far is an example of a particular type of divergence metric. Like it's going to be an example of what we call the KL divergence, right? And so we're going to like try and generalize this objective from the KL divergence to more general divergences and show that that can help with this mode averaging problem, right? So just to like, what do you call it? Preview what the result is going to be at the end of this slide. We're going to show that this maximum likelihood objective is essentially the same as a forward KL divergence. So how many folks are familiar with the KL divergence? Most folks? Ish. Okay, no worries. So the maximum likelihood objective is saying if I sampled S star and A star from D, then maximize the likelihood of pi theta of producing A star given S star. What I'm going to argue is that this thing is essentially some version of a KL divergence between pi expert and pi theta. Okay, and I'll define what the KL divergence is in a second. So that's what the whole slide is going to be. So if you ever look back at the slide, just think of it as all of them are just steps to show that maximum likelihood, optimizing the maximum likelihood is equivalent to optimizing the KL divergence. Okay. So what we're going to say is that so what we're going to say here is that this expectation, we can break it up. So we can say this is going to be the expectation of states drawn from an expert, right? And the expectation of actions drawn from an expert of log pi theta of A star given S star. Okay, so we threw in some new notation here. But essentially what I'm saying is that S star, A star are drawn from an expert. Yeah. And if you have an expert, you can think of a state action pair drawn from an expert by first drawing a state from the visitation of an expert, like what states would the expert go to? And then second is given what state you chose, what action would the expert take, right? So this expectation, which is coming from the expert data distribution, right? D is from an expert. You can think of it as drawing states from an expert and then drawing actions from the expert policy. Yes. So all we've done is we've re-expressed that expectation in terms of this decomposition, right? Find the expert states, then choose the expert actions. Okay. And then I'm going to do a nice little trick of like adding and subtracting. Sorry, guys. My iPad is misbehaving. Well, I'm going to add and subtract. So I'm going to say expectation S star coming from row of S, expectation of A star coming from pi expert of A star given S star. Right? And we had log pi theta of A star given S star. Now remember, you're doing minimization or you're doing maximization with respect to theta, right? So this is the thing you're learning. This is the expert, which is unknown, right? So you don't know the form of the expert. You just have samples from the expert. You don't know the expert. You have samples from it. You know pi theta, or like you know the form of pi theta. You're trying to optimize this objective with respect to theta. Yeah. Okay. So now we're going to like add and subtract a log pi e, A star given S star. Okay. Yes. So, yeah, so you're just going to add and subtract this. And then because this term doesn't depend on theta, right? You can kind of get rid of it. Like it doesn't change the max. Right? If you added something that doesn't change the max, it doesn't affect the argmax, right? So you can just kind of get rid of it. And so now what you have is expectation of states coming from the expert, expectation of actions coming from the expert of if you have log A minus log B, which is equal to log A over B, right? It's like logarithmic identities. So you're going to have log pi theta divided by log pi E. Yeah. All we did is add and subtract. We said this doesn't affect the max because it doesn't depend on theta, right? And so you can now take these two terms and convert log A minus log B into log A over B. Yeah. And so now the overall expression you have is this one, right? The one shown here on the right. Now the definition of the KL divergence between two probability distributions, P and Q, is expectation P log P over Q. Yeah. It's not a symmetric divergence, but it's saying that if I have two probability distributions P and Q, I can measure the divergence between them using a divergence measure like this, right? And so if I do a little bit of pattern matching, how do I convert this objective into this objective? They're not exactly the same. Right? So like note that this is, it depends which one is on top and the bottom. So this is P, expectation P log P over Q. This part is expectation pi E log pi theta over pi E. Right? How do I convert it to a KL divergence? Negative, that's it. Right? And so you can write this as the negative of expectation A coming from pi E log pi E by pi theta. That's it. So now this thing is literally the KL divergence. Right? So you can say that this is essentially the KL divergence between pi E and pi theta. Right? And so you can kind of think of it as you can kind of think of the KL divergence as measuring the difference between two different distributions. And this is just saying you're trying to maximize the negative, which means you're just trying to minimize the average divergence, right? You're just trying to, sorry, I jumped through that part a little bit. So you're trying to say you have a minus, you're trying to maximize the minus KL divergence, which means you're trying to minimize the KL divergence, right? And so you're going to say, I'm going to minimize expectation of S coming from the expert of the KL divergence between pi E and pi theta. Right? So what we've shown is that this objective, maximum likelihood, is kind of the same as the average KL divergence. Yeah. Okay, so now you don't have to go through my messy handwriting. We can typeset things very nice. Oh no. Okay, I may have to reshare. It's still here. Sorry, this never disappears properly. Good, it's gone. Sweet. Okay, so what we've done is we said that's log pi theta. We're going to add and subtract a term. We remove the term that is irrelevant on pi theta, right? And then you can do a little bit of log manipulation, do some little bit of log identities, and we can show that the maximum likelihood objective is the same as minimizing the KL divergence, the average KL divergence over all the states, right? So essentially, intuitively, you can kind of think of this as making pi E as close to pi theta as possible in average over all the states, according to this measure, which we call the forward KL divergence. Right? So you'll note that the KL divergence, this thingy, this measure, KL divergence, is essentially expectation P log P over Q. Right? So this is what you call forward KL. And it's not symmetric, right? Because if you look, the expectations under P, right? So it's not symmetric. Now, if you can have something called the reverse scale divergence, which is expectation Q log Q over P, right? So you'll denote that as DKL QP. And this will be DKL PQ, right? And so it's like swapping P and Q. Right? And so the first one is the forward scale divergence, and the second one is the reverse scale divergence. And we'll show how they have different properties. And the reason it's relevant for imitation learning is one of them does mode averaging and one of them does not, right? And so what we've done here is we've said, okay, maximum likelihood corresponds to a particular objective, which is minimizing the average forward KL divergence. Right? And the forward KL divergence, I'll show in a second, is essentially doing mode averaging, right? Especially when you have a Gaussian. And we can consider other forms of this divergence besides the forward KL divergence, including this reverse scale divergence I talked about, which doesn't have this mode averaging. Yes? So the important bit here is to remember that it's a little hard to think about maximum likelihood as a divergence measure. So we've converted this into a general form of divergences, and we've said that this is an average scale divergence. Scale divergence is one instance of a broader class of divergences, and different choices of that divergence will have different properties. Right? Okay, that's a lot. Questions? Yeah.
The reason it's just a KL divergence is because it uses the log specifically.
Yeah. Right. So it's the KL divergence, which is, should really add the KL divergence here. Is expectation P log P over Q, right? Is one instance of a general class of divergences called the F divergence. And so the F divergence is saying that for any class, I think it's any class of convex functions F, you can define a divergence as expectation Q, some function F, P over Q. And the forward KL divergence is a particular instance of that, right? You can choose different choices of F to get different instances of that, right? But the important bit is that, like, this is a choice of divergence. If you choose a different divergence, you'll get different properties. Okay. Let's see. Do I have? Okay, so ignore all the text for a second. I just wanted to get to this figure. Now, if I have a multimodal distribution, so like ignore this stuff for a second. Just look at this guy here. So if I have a multimodal distribution, right? And at the multimodal distribution, you're using the forward KL divergence on, which means you're saying expectation by E, or sorry, DKL by E by theta, which means you're doing expectation by E log by E by pi theta, right? What's going to happen is that anything which has high likelihood under the expert, but not under their policy, will be penalized a lot, right? Try to think of it like you're optimizing with respect to theta, right? So really what this objective boils down to is like an expectation by E of minus log pi theta, right? Because the log pi E term doesn't matter. It doesn't depend on theta. And so essentially what's going to happen is that anything that has high likelihood under pi E, but low likelihood under pi theta is going to be penalized a lot, right? Because it's something that will show up in your expectation, but your log value will be really small, and which means that your loss will blow up, right? So the important thing to remember here is that the forward KL divergence really doesn't like to miss anything. Like if there's anything that is in pi E, if there's anything in the expert, and it is missed by pi theta, like it doesn't have likelihood under pi theta, like the forward KL divergence is very unhappy, right? Because it's going to blow up because it's saying that for anything that's under this expectation, your log pi theta is, if your pi theta is small, that means your minus log pi theta will be huge, right? And then that's going to like blow up your loss. And so as a result, what's going to happen is you're going to like end up essentially averaging your modes because you really don't want to miss anything in your training data. Right? As soon as you miss anything in your training data, like your log pi theta will be small, which means that you'll blow it up. Yeah. And so, like, that's an intuitive reason why the forward KL divergence or the maximum likelihood objective leads to this mode averaging. Okay, does that make sense? If it doesn't make sense, let's go over it again. Yeah. Quick recap. Okay.
Like
100%. Yes. So what do? We started from the maximum likelihood objective, right? So that is supervised learning right on the top. So you're going to try to maximize the likelihood of expert actions A star on expert states S star. And S star and A star drawn from the expert. Okay. We did a little bit of adding and subtracting and a little bit of log magic to show that this objective is essentially the average forward KL divergence. Right? So we're saying maximum likelihood is equal, or maximizing the maximum likelihood objective is equivalent to minimizing the average forward KL divergence, right? So that's all that this proof is saying. So just jump from here to here. That's it, right? So that's the whole point of the talk. And then we're arguing that the forward KL divergence is one choice of a broader class of divergences. But the forward KL divergence is particularly susceptible to mode averaging because if you look at like this objective, expectation pi e of log pi e by pi theta, right? Anytime you have something which has likelihood under pi e, which means that it's going to be sampled, which means that's in the expert data, but it doesn't have likelihood under pi theta, right? So imagine you considered like a pi theta, which looks like this, right? So it misses a mode. So what's going to happen then is if it misses a mode, this will be under pi e, but not under pi theta. When something's under pi e, but not under pi theta, then this objective, this log pi theta is going to blow up. And it's very unhappy if it blows up, right? So then what's going to happen is you really don't want to have that. And so the objective is going to force, your objective is essentially going to force you to mode average. You want to cover as much of the expert distribution as you can, even if you're averaging modes. Yeah. So, the forward KL divergence will lead to behavior that looks kind of like this. So it's saying, I can't be multimodal because I'm a Gaussian, right? But I really, the objective makes me extremely unhappy if I miss anything in the expert. And so you average the modes. Okay. That was it. Good. Any more questions on the forward KL divergence before we keep going? Yes? Someone want to come up and drive the next one? Okay, so the forward KL divergence is one class of a broader set of KL divergences, or a broader set of divergences, which we're going to call F divergences, right? And so a general F divergence between a probability distribution P and Q is going to be an expectation with respect to Q of F of P divided by Q, right? And so different choices of F are going to lead to different divergences. Right, so I believe that the forward KL divergence is setting F to X log X. Right, so if you can actually derive, like if you take expectation Q, F of P over Q, and set F equal to X log X, you'll get the forward KL divergence. Like the proof is simple. You just say expectation Q of P over Q log P over Q, right? And then you can kind of like do a little bit of algebra here, and you can show this gives you expectation P log P over Q, which is the forward KL divergence. Yeah. So we're not going to derive this in detail, but yeah, go ahead.
Now that you've used the term divergences in a plural, can you tell us what a divergence is?
Yeah, I guess a divergence is something that's like measuring the difference between two probability distributions. And so like it's kind of like a metric that's telling you how different, well, It's not quite a metric in the formal sense, but it's a metric in that it's telling you how different two probability distributions P and Q are.
So it takes us input two distributions and
Yeah.
gives you a real number. Is that?
That's right. That's right. So it's two distributions gives you a real number. And when P and Q are the same, the divergence is 0. Right? And I asked this question on a lot of my interviews, but like you can prove that the KL divergence is positive, right? So you can prove that it's always positive. And so like you never have a negative divergence between two things. And so it's 0 at its lowest. And so they're just like, well, with two numbers, it's easy to kind of measure. With scalars, it's easy to measure how different they are. For vectors, you have to choose a norm. For probability distribution, you have to choose a divergence. It's kind of the same, just measuring the difference. And so what we've kind of showed is maximum likelihood is the forward KL. The forward KL is one instantiation of an F divergence with the F set to X log X. Right? So you have this thingy, like go home, plug in X log X into this thing. You'll see that it gives you exactly the forward KL divergence. Okay? I think it's just like a little tedious to go through in lecture, but you can kind of show that gives you exactly the same. Okay. Now, the nice thing is that you can, now that you've defined a framework like this, you can choose F to be something different. And if you choose it to be something different, then it'll have different properties. Right? So another, like a common one we're going to think about is something we call the reverse scale. Right? And so the reverse scale, as I said earlier, let's say the forward KL is DKL between P and Q. It's the expectation P log P over Q. Right? The reverse scale is just swapping the positions of P and Q. Right? And so the reverse scale is saying the RKL between P and Q is going to be expectation Q log Q over P. Right? And so this one is a lot easier to see. If you set F equal to minus log X in here, you directly get expectation Q log Q over P. And so you set F in here. This gives you the reverse scale. Okay. So the only difference between the forward scale and the reverse scale is that P and Q are flipped. And because it's a non-symmetric divergence, it matters. Right? It matters, and we'll talk about why. Right? So, but let's just make sure we're clear on the definition. The forward scale is the expectation P log P over Q. Reverse scale is expectation Q log Q over P. Swap P and Q. Okay. So why is that going to fix our problem? Our problem was mode averaging. Right? Our problem was we have Gaussian, there's multimodal distribution. We're going to do mode averaging. If you do maximum likelihood is forward KL. Forward KL hates to miss things, and hence it does mode averaging. So why is reverse scale going to fix our problems? Yeah.
Well, in the case of the roundabout, it'll pick one of the two pieces of the paths and go straight to the.
Right. So the hope is that with reverse scale, rather than trying to do mode averaging, it'll do mode seeking. So it'll pick one of the two modes. So remind me of your name? Matthew. So as Matthew was saying, if I have two different paths, I will pick one of the two paths, right? Whereas forward KL will go straight through here. I'll either go left or I'll go right. So let's try and intuit that a little more. Let's try and see, why does the reverse scale solve our problems, right? So I have expectation Q log P over Q, right? And so let's stick that into our imitation learning setting. Let's replace it with pi E's and pi thetas, right? Experts and learned policies.
All right.
Yeah.
You verbally said log P over Q, but you wrote Q.
Sorry, keep that, yes.
Okay. Let me keep it.
It's the lack of sleep.
Okay.
A good catch. So I meant expectation Q log Q over P. And so importantly, here we have the forward KL divergence, which is sorry, give me a second. Let's see, Jesus Christ. These things don't erase for some reason. Okay. And so we'll cover y in a second, but we're going to consider two different things. One of them, which is choosing a different divergence. So as you're saying, choose the reverse scale, or we can choose a more expressive choice of pi theta. Right? And so there's two ways to solve this problem. The mode averaging problem is unique to a Gaussian. Right? It doesn't happen for every distribution. So we can either use the more expressive distribution class, or we can change the objective to a reverse scale, as we'll talk about in a second. Right? And so the point here, what have we done over the last 3 slides? We've shown that maximum likelihood is equal to the average forward KL. We've shown that forward KL is one instance of an F divergence, which is particularly problematic because it does mode averaging. Right? And we've said that there can be other divergences like the reverse KL, which I'm going to state without proof for now, can do mode seeking. We'll talk about that in a second. And the 2 ways to fix this problem are either to use a different divergence like the reverse scale, or to use a richer class of distributions for pi theta. Yeah. And so this it's not a hopeless problem. We actually have a pretty good handle on it. You either change the objective or you change the distribution class. Okay. Yes.
Regarding the changing the distribution class.
Yeah.
Do you mean changing the distribution class of the expert?
Of the learner, not of the expert. Because the expert you don't have access to. All you have is samples from the expert. And so the expert can be arbitrarily complicated. All you have control over is your policy, like as you as in like the robot. Right. And so you can only change pi theta. You have no control over pi e. Right? Because pi e is coming from the expert. Yeah.
Let me know if we're gonna cover this later, but how do we know when to choose to change the divergence and when to choose a different distribution?
Good question. I don't know if I have a silver bullet, but often using a richer distribution is easier than changing the divergence, so do that. It's just more practical. Like we'll cover the different divergence in a second, but often changing the divergence to something like reverse scale is hard to implement in practice, and it like needs a bunch of additional machinery. Whereas changing the distribution class is like go to PyTorch, grab a diffusion model, stick it in your policy, and it's a lot easier. And so in a practical sense, I would recommend actually just using a richer class. But it's cool to study the different divergence, and you get math points. So, all right. So let's
So is the mode seeking versus mode covering that based on just convexity, or are there other properties of law?
In this case, it's based on convexity. I'm not making a general claim about all divergences. I'm just going to make a claim about forward versus reverse. Yes.
For mode seeking.
Mhm.
If you have a symmetric distribution, do you pick like random mode or?
Yeah, you'd pick a random mode. That's right. Yeah. And if you don't, you'd pick the bigger. The bigger mode. Otherwise, you pick that. Yeah. Yeah. Exactly.
The reason that we got a forward KL divergence in the first place is because we decided to stick a log in front of the. Yeah.
It's not so much that like the problem with like it's not that it's a log. The reason it's a forward KL divergence is that your sampling, like if you look at your objective, right? It's like the reason it's a forward KL divergence is because you're sampling from your expert. So if you think of this as like expectation P log P over Q, where P is your expert and Q is your learner, right? A forward KL divergence is when the expectation is under your expert. And a reverse KL is when your expectation is under your learner. And so it's less about the log. The log is just for numerical stability, but it's more about where your expectation is coming from. Right? And so that makes sense? Okay, so I've been talking about reverse scale for a hot second. Let's just get to why it's mode seeking, right? So the first thing we're going to do is we're going to try and go from our forward KL objectives, right? So the FKL between pi e and pi theta is the expectation pi e of log pi e by pi theta. right? So note that this and this, they're not just negatives of each other. They look like they might be negatives of each other, right? Because obviously pi e and pi theta are flipped. But the important thing is that the expectations are under different things, right? So the top thing is under pi theta, which means you're taking samples from your learner. And the bottom thing is under pi e, which means you're taking samples from your expert. Yeah. And so the forward KL divergence, which is the thing we've been talking about so far, is taking samples from your expert, right? So it's doing this offline thing. You take an expert data set, you do supervised learning. The forward KL. Reverse KL is taking the expectation under pi theta, which is the thing that you're learning, right? And so that's closer to an RL style objective, but essentially it's saying when you take samples from pi theta, which is the thing that you're learning, and then you measure how different pi theta and pi e are on those samples. Right? And so it's important to remember that it's not just the negative, the expectation is what really matters. Okay. So if this is our reverse scale objective, let me explain intuitively why it's mode seeking, right? So let's say this was our probability distribution, and we've taken this reverse scale objective, right? Let's talk about why it's mode seeking first, and then I'll say how we can optimize it. So the reason it's mode seeking is that if you remember the forward KL divergence, you had pi e log pi e by pi theta. Anything that was in pi e but was missed by pi theta, the divergence complains, that has to cover everything. That's why it's mode average. Now in the reverse scale, the expectation is not under pi e, it's under pi theta, right? So the pi theta gets to choose what the data distribution is. So the pi theta gets to choose where the expectation is gonna come from, right? So the pi theta gets to choose where you draw samples from. So unlike the forward scale, where the samples are coming from pi e, you have no control. In pi theta, in the reverse scale, the samples are coming from pi theta, right? And if you're choosing them from pi theta, you can concentrate them in the place that has the highest likelihood of pi theta, right? Of pi e. Right? So you're saying that I want to choose samples where pi e is highest, right? And so here what you're saying is I don't want to miss anything that pi e has seen. But here what you're saying is I get to choose what distribution I'm sampling from, right? So I get to choose what the expectation is under. I'm just going to choose the things for which pi e is as large as possible, right? So now mode averaging would be something like this because you don't have control over the sampling distribution. Reverse scale is saying I do have control over where the samples are drawn from. And so I'm just going to pick things where pi e is the highest, right? So the solid line is pi e. And the second dotted line here is pi theta under the reverse scale. So for the reverse scale, because you have control over the sampling distribution, you're okay skipping this thing because it doesn't show up because it's never sampled, right? Whereas if you're doing the forward scale, you have no control over the sampling distribution, so you have to just cover it. Okay, so there's lots of really nice blog posts on this. I'll try to send one on it. It's a little counterintuitive, but just like think about it after class for a second. But essentially, the forward scale with the Gaussian is mode covered, and the reverse scale is mode seeking. Yeah.
So will this always pick the most emphasized mode?
Yeah. Okay. Because the reason is because you're like trying to like minimize this objective. So you're going to try and pick things for which pi e is as high as possible. And so you're going to try and go towards the highest mode. And remind me for name. As Muhammad was saying, if they're equal, then those two, like it has to pick one of them, but it just like does tie breaking there. Remind me of your name. Tree. Okay. So I'm just going to learn all your names over the course of the quarter. But okay. So everyone buy that the reverse scale is mode seeking? Yeah.
So in reverse scale, you're sampling from the policy,
Correct.
which means you have to roll it. Like
Yeah. I'll cover that in a
so
second.
it's sort of like you're saying, I don't like the reverse scale is saying I don't care how well I match the expert overall.
Yeah.
Just tell me how well I'm matching it in the state that I end up.
That's exactly right. That's exactly right. So reverse scale, the forward scale is saying I have to match the expert on the states that the expert visited, and the reverse scale is saying I have to match the expert on the states that I'm visiting. And so that's kind of an intuitive way of thinking about it. That's great. Okay, so the reverse scale is great. Seems like it's going to solve all our problems. We will hit no more trees, right? But what's the problem with reverse scale? Like why I was just remind me for him, orange. David. As David was asking, which one should I use? And I was saying, okay, reverse scale is kind of a pain. Like, why is it a pain? If I just look at that objective, what makes it hard? So now,
You get,
yeah, great. So there's two issues. One of them is how do you get pi e, right? Because if you remember the forward scale objective, we were doing expectation pi e log pi theta. Okay, so you only needed to know the likelihood under pi theta, and you just needed samples under pi e, right? So you have data from the expert. You don't need the likelihood under the expert. You never need to know the form of the expert. But if you look at the reverse scale, you need to know the form of the expert. So you need to know pi e, and you don't have pi e, right? And so that's what makes the reverse scale hard to compute. The second thing that makes it hard to compute is that your expectation is under pi theta, which means that you have to execute in the world, right? Which means you have to take samples from your pi theta, which is more painful than just training things offline. And so two reasons. The first is, the first is that you don't know pi e, and the second is that you're sampling from pi theta. And so both of those make the reverse scale kind of a pain to estimate. Right? So behavior cloning is simple. You take in a bunch of data, you put it offline. You don't need to know any like expert likelihoods. You just need to like do supervised learning. Reverse scale is more painful because you have to like take samples from pi theta in the world. So you have to have access to the environment to keep executing, which might be unsafe or expensive. And you need to know what pi e is, which is kind of a pain. So, because you don't know the expert likelihoods. You don't have access to the expert's brain. Right? So reverse scale is great, but it's hard to estimate. One of my students who just graduated, he wrote this excellent paper on tractable ways of approximating the reverse scale. Right? It's got like a bunch of fancy math, which makes it into a GAN. Really nice paper. Maybe I'll make it one of the seed papers. But it's really nice. We won't have time to go into it, but essentially it gives you tractable ways to optimize the reverse scale. The problem is that it becomes a GAN, and that's a pain. So I think it's great in principle, but hard to do in practice. Yeah. Right. So the first thing we covered is we want to deal with this mode averaging problem. We can change the objective. Everyone kind of followed what I did. All I did is that go from forward scale to reverse scale. Reverse scale is mode seeking, but it's harder to implement. Okay. The second thing you can do is perhaps a little more straightforward, which is to make pi theta more expressive, right? And so instead of using a Gaussian, we've been assuming Gaussian throughout, we can use things that are not Gaussian, right? So we can say that like, what if we used more expressive probability distributions, for instance, mixtures of Gaussian, latent variable models, autoregressive models like transformers, diffusion models, so on, right? Like all of these things that are meant to deal with multimodality. So essentially what happened is the behavior cloning people looked at all the generative modeling people and they're like, oh, these people do multimodality. So let's just steal all their models, right? So each of these is an example of a model from generative modeling. Right? So generative modeling is often concerned with density estimation for multimodal distributions, like complex distributions which have like distributions of molecules or distributions of images or text, like they're inherently multimodal. And so we basically like import those models into imitation, right? Okay, so your homework will have a few of these, but let's just kind of run through what a few of these look like. I won't get too much into the detail of each of these. We'll cover diffusion models and transformers later in the class, but we'll just go over them a little bit. Okay, but the premise is this mode averaging problem, right? This mode averaging problem is kind of unique to Gaussians. This only happens to a Gaussian, but if I have like a more expressive distribution, let's say I had a mixture of Gaussians, let's say I had two Gaussians in a mixture, I could like hit this objective. It's not that I have to average them all. I can like drive that to 0 for this distribution, right? And so I think someone asked me this question last class, but why don't we just use a more complex distribution all the time is because often they're computationally more expensive, and sometimes they're less stable and hard to train, right? Okay, but let's start with the simplest one, right? So how many folks are familiar with mixtures of Gaussian? Most people? Good. So we'll keep it short. Basically, your neural net, instead of outputting the mean and variance of a single Gaussian, you pick a number of Gaussians, you output the mean, variance, and weight for a mixture of Gaussians. And so you say that your probability distribution is like a weighted sum of likelihood over a mixture of Gaussians, right? So this mixture weight, these things have to sum up to 1, right? Or they're normalized. And these things are like Gaussians, right? So you just need to show that this thing integrates to 1. But essentially what this allows you to do is represent distributions that look kind of like that, right? Where the Gaussians can go up or down. Now, the tricky part in using a mixture of Gaussians is that you often don't know how many mixture elements you have, right? So it's like, I don't know if humans are 3 modal or 10 modal or 2 modal, like it's hard to estimate. And if you get the modes wrong, it gets hard to optimize. So if you're under choosing the modes, you're going to start averaging. And if you're over choosing the modes, you're going to have all of these redundant modes and optimization gets hard. And so the tricky part in using mixtures of Gaussians is that it's like hard to choose the number of modes. Yeah. Like sometimes the optimization gets like stuck. Like the optimization gets stuck with all the modes because it's in linear function approximation. Like the optimization gets stuck where all the modes get clustered in one. I don't know if I have like a great theoretical explanation, but empirically this happens sometimes. Okay. The next one is autoregressive models. So mixtures of Gaussians are just, continuous distributions. You're just going to mix a bunch of different Gaussians. One that I particularly like is called autoregressive discretization. And so the idea behind autoregressive discretization is that categorical distributions are great at being multimodal, right? So if I have, if I have a categorical distribution, right? Like this, like a discrete distribution. A discrete distribution is inherently great at being multimodal, right? It's like a table. Like a table is not unimodal. I can have some values be really high. I can have some values be really low. And so if I want to fit anything, like a discrete distribution is great. Discrete distribution is naturally multimodal. It's simple, cross entropy loss. It's nice. Now, what's the problem with the discrete distribution? Like why can't I use it for all of my robotics problems?
You could find like appropriate discretization.
That's right. That's right. So you have to find an appropriate discretization, right? So if I had a one-dimensional action, if I just go forward and backward, sure, I can like split the bins up according to the range of values I'm going to take. But imagine I had a robotic arm, right? Robotic arm has 7 degrees of freedom. And if I'm trying to discretize 7 degrees of freedom, let's say I had 100 bins per dimension, I'm going to have 100 times 100 times 100 times 100 times 100, right? So it's going to become exponentially many bins. If I think of discretizing multi-dimensional vector space, I'm going to have like exponentially many bins. And that makes like optimization hard, makes exploration hard. It just kind of becomes, your memory becomes too large. It's just like not a feasible solution for any higher dimensional system, right? So if you have like something that's going left and right or up and down, like go discrete, it works. But if you have anything that is a higher degree of freedom system, it's hard to just go discrete, right? And so what the idea behind autoregressive discretization is it's going to do dimension by dimension discretization in a way that scales linearly rather than exponentially, right? So when I say exponentially, I mean that the number, like let's say I have a 10-dimensional space, 100 bins per dimension, the number of bins you're going to have is 100 to the 10, right? Yeah, 100 to the 10. And what I'm going to suggest is a method that makes it 100 times 10, which is a lot more scalable. Yeah. Okay. So how many folks are familiar with chain rule of probability? Ish? Yeah. So the chain rule just says if I have a probability distribution x, y, z, I can write this as p of x times p of y given x times P of Z given X comma Y, right? So you can just separate it into like different factors as long as they're conditional on the previous factors, right? And so what autoregressive discretization is going to do is going to provide you a technique to compute these likelihoods, but do it using the chain rule in a way that does not scale exponentially poorly. Okay. And so does the chain rule make sense? Just you can extend that to R, like it doesn't rely on the Markov property or anything. It's just true for all probability distributions. Right. So just saying like the Markov property, for instance, would say it's P of X times P of Y given X times P of Z given Y. No dependence on X. But this is just the chain rule is true for everything. Okay. So what we're going to do is we're essentially going to use the chain rule to use categorical distributions for high dimensional systems. Okay. And so let's think of it as the following. You're going to have a k-dimensional action. Okay. So you're going to have P of A1, A2, A3 till AK given some state. Right. And so these are all essentially like different, like you can kind of think of all of these as different elements of a vector A. Right. So you have multi-dimensional action. Let's say it's the like action at each of the joints, right? A1 is joint 1, A2 is joint 2, A3 is joint 3, A4 is joint 4, etc. Right? And so essentially you have k-dimensional system, for instance, 7-dimensional arm. A1 to AK are the values of the action at each of the dimensions. Right? They're not across time steps, they're just different elements of a vector. Okay. And now what autoregressive discretization is going to do is going to use the chain rule here. So it's going to say, I can express this distribution as P of A1 given S times P of A2 given S and A1 times P of A3 given S, A1, A2, all the way till P of AK given S and A1 to AK minus 1, right? You just like multiply all of these together. Right? So all we've done is we've taken that distribution, which is likelihood of all of those actions happening, which are just different elements of like a vector space, right? A vector space is each of the dimensions of your arm, for instance. And we've said that the likelihood of that action being taken at that state is the likelihood of the first dimension being taken given the state times the second dimension given the state and the first dimension times the third dimension given the state and the first two dimensions and so on, right? So it's just applying the chain rule directly to that probability distribution, which is, this is essentially your pi theta of A given S. Okay? It's your probability of your actions given your state. Okay? So all we did, we took that action distribution, we used the chain rule. Okay. Now, what makes autoregressive discretization cool is that each of these distributions we're going to represent with a categorical distribution, right? So it's like, remember that each of these distributions are essentially a distribution over a one-dimensional variable, right? So like P of A1 given S, A1 is a scalar. A1 is like the first degree of freedom of your arm. A2 is a scalar, it's the second degree of freedom of your arm. A3 is a scalar, it's the third degree of freedom of your arm, right? And so each of these distributions is a scalar. And so each of them can be represented as a categorical distribution, right? And so each of these is going to be a discrete distribution. So it's kind of shown over here on the right. It's like each of these is going to be a discrete distribution. Does that make sense? So each of these is scalar, and each of these will be a categorical distribution. And the important thing is that when you, just like a transformer, just like a RNN, when you like produce an action from the first dimension, it goes in as conditioning to the second dimension, right? And so the important thing here is that you, like the way you're going to generate from this autoregressive model is you're going to start by generating A1 from a categorical distribution, right? Then you're going to take the output and stick it into the neural net that represents A2. You're going to take the output of the first two and stick it into the neural net that represents A3, right? But in terms of like, and so you have like k different neural nets, right? Or you could have like a recurrent model. But the point is that each one of them is just discretizing a scalar, right? And so the reason it's called autoregressive is because you have to generate the first, feed it in to generate the second, feed the both of them in to generate the third, repeat, repeat, repeat for k dimensions. Okay, it's a little bit counterintuitive, but the important part is that what we've done is we've taken this, like, if I just directly discretize this like k-dimensional thing, I have to like find all the bins in a flat way, I have an exponentially large number of bins. Okay. But instead, what I'm going to do is I'm going to discretize dimension by dimension by dimension. I'm going to take the output of the first dimension and stick it into the second dimension. And take the output of the second and the first dimension, stick it into the third dimension, right? So I'm going to have, you know, k different encoders, but each one is going to take the output from the previous. And so that's what's going to let you like scale up to high dimensions while being expressive, because each one of them is a discrete distribution, right? So as you can see here, each of these is discrete, which means that you can be multimodal. So you can capture like a complex multimodal distribution with just a bunch of categoricals, right? If you wanted to be like, so this is kind of how the math works. The easiest way to think of this is you can just think of this as a big transformer, which is like discretizing things per dimension.
Sorry, just a step in there somewhere.
Yes.
When you say you're feeding it into the next one, you mean you're taking the argmax of the distribution and the prior step?
Yeah, exactly. Or you take a sample.
Oh, a sample, I see, I see.
Right. So, so in autoregressive distributions, you're going to have a slight difference between training and testing. So in training, you know what A1, A2, A3 are. So you can like directly stick them into your models. But during sampling, when you're trying to generate something from here, you're going to take your S, you're going to get a distribution, you're going to take a sample from this categorical distribution. And then the sample is going to go in here. And so the trade-off here is that your action generation process is not just one forward pass. You have to go through k forward passes. And so it's like a more expensive generation process.
In terms of performance, how does this, like, are we trading off anything between this method and creating a flat discrete representation of all the dimensions?
What you're trading off is memory versus compute. And so you can think of a flat discretized thing as fast in terms of compute, because you can just generate it once. But it's slow in terms of memory. Because you have like your neural net is huge now, because you have exponentially many things. Whereas here, you're saying the memory is controlled, because you're just doing it one dimension at a time, but the computation is larger because you have to do it one dimension at a time. So you're just trading off memory.
In terms of accuracy, not just sacrifice.
No.
So about accuracy, when you're training the first thing as a neural network, and the second thing as a separate one. Your test times, you're sequentially executing these one after the other.
Yeah.
Each of them could have like some epsilon error. Wouldn't that, like, once the first one makes some epsilon error?
Yeah, that's a great
like,
point. That's a great point. So what you could have is that you could have like this one could generate something that's a little out of distribution for this input, which is like kind of the same problem as compounding error. The reason it doesn't happen is because it's discrete. And so unlike a continuous space where things can go out of distribution more, it's like there's only k bins, right? And so you would have seen that bin somewhere. Now it certainly can happen because the number of combinations gets larger and larger, but less of a problem. Good question. Okay, so let's zoom back out. The point here is that we want to deal with multimodal distributions. We talked about mixtures of Gaussians. They're great. Hard to choose the number. Autoregressive discretization is a different choice, which uses dimension by dimension by dimension discretization. The trade-off is memory versus compute. Right? And so you're going to say, I'll discretize the first dimension, sample, stick it into the second dimension, sample, stick it into the third dimension, sample. Right? So you can kind of think of it as a sequence model, which is generating discrete distributions one by one by one. Yeah. Okay, this is going to be in your homework. So if you don't get it, that's like a lot of pain. So please ask me questions now. And we can. I find those. Yeah.
In the case of example,
Yeah.
Does it matter the order that you pick them?
Excellent question. Definitely does. The problem is it's like not easy. Like it matters because the choice of conditional distribution is often different depending on the ordering. So like some things will obey like causality. Like for instance, in a kinematic chain, you want to like go from the top down. Like you want to start from the first thing and the next because they're all connected in a certain way. Now, if you like flip it, you can still represent the probability distribution. It's just like less simple. And so as a result, the resulting policy generalizes worse. And so the order does matter. The problem is it's hard to determine a priori. And so I think it's a good open question.
And what if you can't define an ordering over them because of constraints in your system that require you to choose them jointly, where you can't really have a single ordering that allows you to do this?
So you're able to represent any arbitrarily complex joint distribution because everything is conditioned on everything in the past, right? So eventually, like you're not losing expressivity in terms of the joint distribution because of this conditioning. Now, if I had not done this conditioning, right? So it's like this thing is not just conditioned on this, it's conditioned on everything in the past. And so if I hadn't done that conditioning, I would lose expressivity. But here I'm not losing expressivity, right? And so like you don't lose any expressivity, you just lose time. Okay, let's keep going. This is all the rage nowadays, but you can use diffusion models to do imitation learning. Diffusion models are a little different than autoregressive models, but they're quite related actually, in that they're like trying to they try to learn multimodal distributions by noising and denoising a data distribution. So you start from an image, you noise it to noise, and then you learn how to denoise it back to the image. Right? And so diffusion models are going to be able to represent like pretty complex data distributions because they don't try to like, you can show that they don't try to represent like a normalized probability distribution, but rather an unnormalized one. And that lets you like represent more complex distribution. So essentially, if there's distributions that look kind of like this, which are multimodal, you want to go different. Like sometimes you want to go up, sometimes you want to go down. Like diffusion models are great at representing them, right? So I'm just going to leave it at the abstract for now. We'll get into the details properly towards the end of the class, but think of diffusion models as just a way to like estimate the direction to move in, and the direction to move in allows you to have like multimodal data distribution. So the example on the right. So the example on the right shows like diffusion process, which starts from noise and goes to like multimodal trajectories. And so, yeah, the diffusion models are great. They scale a bit better with dimension than autoregressive models do. And so if you're thinking about like relatively high dimensional systems, I think a diffusion model scales better with dimension than the autoregressive one. And Jacob is implemented in the homework. And so you guys have an opportunity to try it out. We'll have more details there. Okay, so that was about underfitting, right? So the key points we covered for underfitting were that we can either solve it by using a richer policy class. So we can say we'll use a mixture of Gaussians, an autoregressive model, a diffusion model, and that's going to make our fitting problem easier at the expense of computation. Or we can try changing our divergence to something like a reverse scale, but that comes at the expense of being harder to compute, like harder to compute under the same assumption, right? And so if I want to solve the underfitting problem or the multimodality problem, that's how I would solve it. Yeah, everyone with me? Okay, so the next thing we want to cover is compounding error. And what does compounding error mean, right? So compounding error, we said, was you make a little mistake, the little mistake becomes bigger, the little mistake becomes bigger, 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 and does quadratically bad with horizon, right? And so we want to kind of deal with that. And so there's like this really cool example from NVIDIA back in 2016, where they got this autonomous car to drive around New Jersey with imitation learning, which is a little suspect. It actually does. And so
Holy cow. Whoa. Whoops. Wrong way.
that's behavior cloning.
Ooh.
So you can see that behavior cloning has lots of problems. But they did like magic sauce, which we'll talk about in a second. And Alright, I think I guys get the idea. So, what is the magic sauce to make that happen, right? I think the idea was actually super cool. But essentially they're saying, okay, like the reason you started drifting off the road was if you drifted a little bit, you hadn't seen that, drifted more, drifted more, drifted more. And they had like a really clever trick to deal with it, which was instead of having one camera, it's going from camera images to action, like that, right? Instead of having one image, they had 3 images, right? So they said, hey, like my car is going to have a camera in the front, but it's going to have a camera which is facing left and a camera that is facing right, right? So it's going to have 3 cameras. And so you can see that the car sees 3 cameras, left, center, and right. Yeah. And what they're going to do is for the center camera, whatever, like you label the actions as they were, but for the left camera, so left camera, you're going to label the actions to go more to the right. And for the right camera, you're going to label the actions to go more to the left. Right. And so the important part, the reason this works is like the left camera is seeing what would have happened if you were swerving a bit to the left. And it says that if you're swerving a bit to the left, go back to the right. And the right camera is seeing what would have happened to the right. If you're swerving a bit to the right, go back to the left, right? And so essentially what you're doing is you're augmenting your data. So normally imitation learning would just see the center camera. It's never seen things that swerve left and right. But what you've done is you've augmented your data so that you have images to the left, going back to the right, images to the right, going back to the left, right? And so now you have this data, which is essentially corrective. So it's saying that if you had swerved to the left, go back to the right. If you had swerved to the right, go back to the left. And that kind of brings you back to your data distribution, right? So going back to our example here, like what that does is it says that, hey, like if you had swerved off this way, go back this way. If you had swerved off this way, go back this way, right? So essentially it's giving you things that go back to the data, right? And so if you're going back to the data, then you're like essentially stabilizing back to the path that you know. So remind me of your name? Thomas. As Thomas was saying, what happens if you go out of the data distribution? I don't know what to do. Like what they've done here is they've augmented the data distribution, so you do know what to do when you swerve to the left or to the right. Yeah.
Can we interpret it as giving it 3 training trajectories, one on the left?
Yes, exactly.
and
Exactly.
the different trajectories?
That's right. That's right. So it's just obviously this is not going to work for every system. This is like particularly specific to these cars, but I thought it was like extremely clever on that particular problem. But the important part is that the important thing to remember is they've taken the base training data and they've like shown you how to like, you have compounding error, but it's shown you how to go from the thing that is far, it's going to like send you back. It's going to send you back in distribution. And so in this case, it is with this like clever data augmentation trick. But more generally, you want labels that bring you back to the data, right? And so you want labels that are going to say, hey, I'm like out of distribution, I want to get back. Now, whether that's through data augmentation or through some other scheme, it's like things that bring you back in distribution so you can keep acting, right? So to Thomas's point from earlier, you don't want to like freak out when you're out of distribution. You want to just come back to the data where you know how to do things. And so essentially, the essence of all methods that try to like fix this problem are try to get back to the data as soon as you can. And so if you've gone out of distribution, try to get back to the data. Okay? And whether that's through control theoretic methods, whether that's through data generation, whether that's through augmentation, whether that's through human labels, like essentially all of them are trying to get you back to the data. So if there's one thing you like take away from imitation learning is just like only trust your data and get back to your data all the time. Okay. So the key insight that we're going to try and take is that we're going to take pi theta, and we're going to say that, hey, when you rolled out pi theta, you had compounding error, so you got to p pi theta. But what you really wanted to get to was p data, right? So p data was where like the training data that you had. You really want to make p pi theta equal to p data, right? Which means that you want to like take your policies and bring them back to the training data. And so the only thing you can trust is the training data. And you want to make the things that you get under your policy as close as possible to the training data. You want to bring them back to the training data. Right? So the way to deal with compounding error is just like anytime you go out of distribution, find a way to get back to the training data. Right? Find a way to get back to the training data. Does that make sense? Okay. So there's like a pretty rich space of theory on this. We're not going to cover it. We're just going to cover the algorithms. But I recommend Drew Bagnell. Like he has a lot of really excellent work on this. And you guys should read it. Okay, but there's a really popular algorithm called Dagger or dataset aggregation, which essentially tries to like instantiate this intuition, which is can we make P data, which is like the training data distribution, as similar as possible to P pi theta, which is the distribution you see when you roll out your policy. Right? And so all that Dagger really says, Dagger is super easy. It's saying rather than being clever about P pi theta, what if you just change P data, right? So what you're going to do is essentially you're going to, you're going to run pi theta in the environment. So you're going to train your policy. You're going to do behavior cloning. You're going to train your policy. You're going to run your policy in your environment. And what you're going to get is you're going to reach some series of you're going to train pi theta using behavior cloning, and then you're going to run pi theta in the environment to reach some series of states, O1 to OM. Okay, and these states may not be expert states. They could be non-expert states. So maybe this was your training data. You train pi theta and you ran it and you reach some other set of states. Okay, so that's going to be your d pi. And now what you're going to do is you need to find ways to go from d pi back to your training data. Right? And so the way you're going to do it is you're going to say, hey, human, look at my d pi and label what the optimal behavior would have been. Right? So it's saying that, hey, like I swerved off the path. Now I'm over here. Ask a human labeler for every state in d pi, like ask the human to, do something optimal, and that'll bring you back to the path with known data, right? And then you can take that additional data, mix it in with your original data set. So you said, the important thing is you roll out your policy to get d pi. It's going to be a set of states. Those states are not going to be good states. But you're going to then ask a human who's an expert to label these states with optimal actions. Okay, you're going to get optimal actions. So you're going to have like O1, A1, O2, A2, or A1 star, A2 star, etc. You're going to take all of these, you're going to mix it into your original data set, and you're going to retrain behavior cloning, right? And you'll retrain behavior cloning, you'll get a better pi theta, you run it again, you do the labeling process again, you re-add the data, and so you repeat, right? So an intuitive way of thinking about it is, this was my training data. I failed and I went over here. Now I ask the human to label all of this. Now this is my training data. And the next time I fail, I might go over here and I ask the human to label it. And this is my training data. But eventually those two things converge. And you can show that you get things that scale linearly with horizons rather than quadratic. Yeah. Go ahead.
So, the expert doesn't try to bring it back to the original thing. It's expert could just give you some.
That's right. That's right. I think that's mostly for intuition. Yeah. So the expert doesn't have to bring you back to the data distribution, although it could. The expert just has to act often. So all we're going to do in data set aggregation is you're going to say, train behavior cloning, run behavior clone policies in the real world, right? You have to run these in the real world. You have to have a human say, I'm going to go to these observations and I'm going to like label them with optimal actions. I'm going to take that new data set that I get, aggregate it with my previous data set, retrain. You repeat, and then great success. And so that's it. Yeah.
So I might be thinking about this wrong, but now that we have diffusion models, is there a reason why we would still use this instead of?
Yeah. So diffusion models are nice because they so lots of people have been trying to like connect diffusion models to Dagger. That's been a thing that's been explored, but diffusion models, they don't respect the dynamics of the system. So when I say take an image and I noise it, like that's going to like garbage noise. It's not going to like perturb states, right? According to the true dynamics of your system, because it's not like you're going from an image of a forest to like gibberish. You're going from image of a forest to a different image of a forest, right? And so the difference between a diffusion model and this is just like, what is the noise distribution? Like one of them obeys the dynamics and one of them doesn't. A great question. Yeah. Okay, so Dagger works. So this was an example from Stefan Ross and Drew Bagnell and others at CMU. And they were trying to navigate this forest with the drone. And they found that without Dagger, you often crash into the trees or you go overly slow. But if you're able to just do this repeated data aggregation process, you overcome a lot of these compounding errors and you could fly around for a pretty long time, right? So the algorithm is dead simple. The policy is trained with BC, you roll it out. The expert sees what states you went to, labels them with optimal actions, you add that to your data set and you repeat, right? That's it. And so that's the premise of Dagger. The question?
A very simple question. In Dagger, are the human reacting to the unfinished state?
That's a great question. That's the next thing I was going to talk about. So the two challenges in Dagger, and I'll leave you with this, is that firstly, you often ask the human, like, because you have to see all of the states that the policy is going to get to, you ask the human to label the things after the fact. So like a human will take the videos of what you saw and label them after the fact, which is kind of a pain in the ass, right? And then the second is that you have to like get a human to sit and label all the actions, which is also a pain. And so both the fact that it's after the fact and that a human has to do it are a pain. And the next couple of things we'll talk about kind of resolve that. But yeah, so there's some techniques which try to do blended control, which like people are controlling the drone along with the AI system, but often you have to label things after. And that's what makes it hard. Okay, let's end there. So Dagger is great, had some problems. We'll cover that next time. Right. Thanks, folks. Have a good weekend. Yes.